Ladies and gentlemen, good afternoon to you all. My name is Irfan Siddiqui. I'm currently the chair of the Department of Physics at the University of California, Berkeley. And it is an absolute pleasure to welcome you this evening to our annual Emilio Segré lecture. Berkeley Physics has a distinguished history marked by both world-class research and service to the public, and in particular to higher education in the state of California. We are proud to be part of the world's finest public universities. Our department's rich history includes Ernest Lawrence's invention of the cyclotron, giving birth to the field of high-energy physics. It includes Robert Oppenheimer, who attracted to Berkeley a generation of brilliant theorists. And it includes the person we honor tonight, experimentalist Emilio Segré. Each fall, we celebrate Segré by bringing to Berkeley renowned experimentalists since 1987. These scientists, through their research, have changed the way we perceive the world around us. Past Segré lectures have included Nobel laureates Bert Richter, Masatoshi Koshiba, Stephen Chu, Hans Bethe, Art McDonald, Dave Wineland, Rainer Weiss, Taka Kahita. And past lecturers have also included Mildred Dresselhaus, Robert Sokolow, Xiaowei Zhuang, and our colleague and former chancellor of the University of California, Berkeley, Robert Bourgeois. Segré received his doctorate in July 1928 from the University of Roma, working with Enrico Fermi. After 2 years in the military, he returned to Rome, becoming an assistant professor in 1932. And in 1935, Segré became professor and director of the physics laboratory at the University of Palermo. Soon after he made his first visit to Berkeley, Segré gave a strip of molybdenum, shown here. Now, in my point of view, molybdenum is a perfectly good superconductor. It should not be altered. It should be used in superconducting experiments, but we'll give Segré a pass on this one. So he gave this molybdenum to his colleague Lawrence, who irradiated it in his cyclotron. And in Palermo, Segré and his colleague, Carlo Perrier, extracted from that strip a previously unknown and unstable element known as technetium. This was the first discovery of an artificial element, an element absent in nature. 15 years later, technetium was detected in stellar atmospheres, proving that certain stars continuously synthesize these heavy elements. In the summer of 1938, Segré returned to Berkeley to continue his work. While he was in the US, Mussolini's government passed laws that barred Segré and others of the Jewish faith from universities. Lawrence offered Segré a position as a research associate. Segré accepted and brought his wife and young son from Italy to join him. With the war depleting Berkeley's faculty's ranks, Segré became a lecturer in the Berkeley Physics Department in 1941. In 1943, he accepted Oppenheimer's invitation to join the Manhattan Project at Los Alamos, where he headed a group measuring fission rates. He returned to Berkeley after the war ended. In 1955, Lawrence and his colleagues designated or designed the Bevatron to produce 6 GeV protons, an energy sufficient to produce proton-antiproton pairs and proton collisions with a stationary target. Later that year, the discovery of the antiproton was announced in a paper by Chamberlain, Segré, Wiegand, and Ypsilantis. Chamberlain and Segré were awarded the Nobel Prize for this discovery in 1959. Segré continued teaching and his research at Berkeley to and beyond his retirement in 1972. Over his 5-decade association with Berkeley, Segré trained 30 PhD students, including C.S. Wu, Herb York, Tom Ypsilantis, and Professor Herb Steiner, who is here. In 1989, at the age of 84, Emilio Segré died from a heart attack while walking near his home in Lafayette. Segré was an avid photographer. After his death, much of the physics collection was donated to the American Institute of Physics, preserving a record of physics before, during, and after the war years. It is my pleasure now to introduce our 2024 Segré speaker, Dr. Pablo Garrido Herrero, and for this task, I would like to call upon Professor Michael Cromie to come to the lectern and introduce our speaker and shepherd the rest of this evening's proceedings.
Hi there. It's my pleasure today to introduce Professor Pablo Herrero of MIT for the Segré lecture. Pablo is currently the Cecil and Ida Green Professor of Physics at MIT. He received the equivalent of a bachelor's in physics from the University of Valencia, Spain in 1999. He then spent 2 years at UC San Diego, where he received a master's degree before going to Delft University, where he earned his PhD in 2005. He worked as a postdoc at Delft and Columbia before joining MIT as an assistant professor in 2008. He was promoted to associate professor of physics with tenure in 2015 and full professor of physics in 2018. He has won many awards. He got all the Young Investigator Awards. I can't list them all, the NSF, the Sloan, the Packard, he got them all. And then more recently, he was awarded the APS, American Physical Society Berkeley Prize in Condensed Matter Physics in 2020, the Wolf Prize in Physics in 2020, and he was elected to the U.S. National Academy of Sciences in 2022. Pablo is a pioneer in the study of nanoscience and 2D materials, and he is a master of incorporating novel materials into tiny electrical devices where their quantum mechanical behavior can be probed using electrical current, electric fields, and light. One of his biggest discoveries was to show that extraordinary things happen when you put two pieces of graphene together and put a small twist angle between them. The resulting two-dimensional moiré pattern allows the graphene properties to be tuned in ways that really surpassed everyone's expectations. This work was done in 2017 with Yuan Cao, who was a graduate student with Pablo at that time, and Yuan is now a professor here at UC Berkeley in the EECS department. And when those results were published, they went off like a bombshell in condensed matter physics, and they have subsequently evolved into one of the most active and exciting areas in our field. One last thing I want to mention is that Pablo is the founder of the Heising-Simons Rising Stars conferences, which provide unique opportunities for young women physicists around the world to come together and discuss their research and future careers. And we hosted one of these workshops here at UC Berkeley last year, and it was a great success. We actually hired 3 of the participants as new faculty members in the physics department. So tonight, Professor Pablo Herrero will present magic angle graphene, the twist and shout of quantum materials. So let's welcome Pablo.
Hello, everyone. Thank you very much for the invitation. It's really a great pleasure to be here. You know, I have come to Berkeley many times. It's one of my favorite universities, the most beautiful campus, I think, in the US. And I have lots of friends, so it's really a pleasure to be here. It's also a great pleasure to honor Emilio Segré, a great scientist, who did so many contributions. We're going to say something about it, but Irfan already mentioned most of the things. I particularly like this, anti-proton discovery was something which, you read in textbooks, and it's like, wow, so great. So really an honor to be here, and I want to thank the invitation from Irfan and Mike and everyone, the whole physics department, families, friends, everyone here. Really, really great. I want to tell you about magic angle graphene and how it has become the twist and shout, of quantum materials. But I know that this is a very, it's a public lecture generated audience, so I want to start, from very basic stuff, okay? So I want to start with the following question. What determines the properties of materials, okay? And, you may think that, as a first guess, the chemical composition is very important. And that is right. For example, you take gold, it is a good metal, okay? You take a different element, aluminum, it's also a good metal, but it's a superconductor when you cool it down. Gold is not. You take, for example, iron, is a metal, but it's a ferromagnet, it's not a superconductor. And you take, for example, silicon, and it's a semiconductor. And as you can see, all of these materials are used, broadly, in technology nowadays. And so chemical composition is obviously very important. However, is that all? Let's take now, for example, carbon. Yeah? Carbon is an element, the periodic table. If you make graphite, which is entirely made of carbon, you have an electrical conductor, but you can also arrange carbon into diamond, and it is an electrical insulator. So it's not just the chemical composition that determines the properties of a material. Something else must be playing a role. Otherwise, we wouldn't be able to get electrical conductors and insulators with the exact same type of atoms, carbon. And indeed, both graphite and diamond are made of pure carbon. So why do they behave so differently? It's because the carbon atoms in graphite and in diamond are arranged differently. We say that they have different crystalline structures. Now, graphite is made of two-dimensional sheets of carbon atoms. Diamond is more of a covalent network of 3D atoms arranged. Now, both crystalline structure and chemical composition are important aspects that determine the properties of materials. Yeah? And for a given material, nature, and I mean the laws of thermodynamics, usually determine what is the most favorable structure, crystalline structure. And there is usually not too much you can do about it. Yeah? Usually the crystal structure cannot be easily changed for a given material unless you do something dramatic, like subject it to extreme pressures and things like that. That was the case until 2D materials appeared in the market. So what I want to tell you about today is the following. I wanted to start with the twist, and for that I will introduce 2D materials, Legoland and Twistronics, and then we will look at a particular case of these 2D materials, graphene and magic angle graphene superlattices. And then we'll go to the shout, which is what happened when we started to look at these materials. Particularly, I'll tell you about our discovery of correlated insulators and superconductivity. And then I'll tell you a little bit about moiré quantum matter, this new field, and an outlook and what has happened since the original discovery. So let's get started with 2D materials. Huh? Now, what do I mean, first of all, what do I mean exactly by 2D? Okay? Well, take a deck of cards. Okay, clearly this deck of cards has, is bulk. It has length, width, and height. Okay? Now, a deck of cards, you can extract one card from the deck, and that starts to look more like 2D. It mostly has length and width and just a little bit of height. Yeah? So let's do the following experiment. Let's imagine that we take an apple, okay, clearly three-dimensional object, and now we slice it into tiny slices. And I get a slice of an apple here. What do you think this slice of apple tastes like? Does it taste like an apple? Probably, right? So what I'm going to tell you about today is that with these 3D materials, when you take a slice of it, its properties can change dramatically. It would be like if this slice of apple actually tasted like a slice of orange or something like that. Yeah? Completely change its properties. And that's going to be already from 3D to 2D. Then when we put two 2Ds together and we twist, it's going to be even more dramatic than that change that I just mentioned. So which material are we going to be mostly looking at? We're going to be looking at graphite. Graphite is the material which is at the tip of your pencils. Turns out graphite is like a deck of cards. Okay? When you write with a pencil on a sheet of paper, it is like if you took a deck of cards and you do, and you spread the cards on your sheet of paper. Okay? That's what you're looking at, a trace of this deck of cards. So graphite under a scanning electron microscope, it looks like this. You can see already here that there are some layers. Okay? These layers are actually quite thick. You can zoom in a bit more, and you see more layers and more layers. Okay? And if you look really at the top layer, you would see that you form these honeycomb of carbon atoms, which we call graphene. Okay? So graphene is a single atom thick sheet of graphite. Okay? It's about 100,000 times thinner than the diameter of one of your hairs. Okay? So it's extremely thin. Okay? It's the thinnest material that exists and that will ever exist, because we cannot make anything thinner than 1 atom thickness. So it took a lot of creativity to discover this graphene. This is a picture of Andergheim and Kostyantov, the two scientists that discovered it. And it took a lot of creativity because there was a theorem, well, there is a theorem in physics that says that graphene should not exist. Okay? It's forbidden, As usual, mathematical theorems do not always work, okay? So actually, these two gentlemen, they were very brave and creative. They disregarded mathematics and said, why not? Let's give it a try. I don't think this theorem is correct. Let's see if we can make graphene. And it was especially creative the way they obtained the graphene. All they needed to isolate graphene was Scotch tape, literally, okay, and graphite powder. Okay? So how did they do this thing? They did the following. You can take graphite flakes. That's, by the way, my hand, actually. And you can take a piece of a Scotch tape, and you sort of put a graphite flake on this piece of Scotch tape, and then you do like this, and you separate it. And you see the flake splits into two pieces. Okay? Then you shift a little bit the tape, you do this again, and you split it into 4 pieces. You do this again, 8, 16. You do this until you get bored, more or less, okay? Or until you cover your piece of Scotch tape with a lot of graphite flakes. And then you take a silicon substrate, and you put the tape on top, facing down. You massage it a little bit, and then you peel the tape, as we have done here. And it turns out that almost magically, what you see in this piece of silicon is that there's a whole bunch of graphite pieces, but every now and then, there is a piece with just one layer of graphene on top. And these pieces look like this. This is monolayer graphene, 1 atom in thickness, next to a 3-layer graphene piece, okay? This thing you can see just with your bare eye, amazingly, even though it's only 1 atom in thickness. You can see it with your bare eye. Okay? So for this very creative way of isolating graphene and for the initial pioneering discoveries, which, by the way, if you look at with a transmission electron microscope, this is what you would look like, okay? It's carbon atoms, Andrei Geim and Kostya Novoselov received the 2010 Nobel Prize in Physics, okay? So for the isolation of graphene and the pioneering initial experiments that they did. So, but let me go back a few years, actually, In 2005, I finished my PhD. This is the way I look back then, I did my PhD in this tiny town, Delft, in the Netherlands. Super beautiful, cute town with channels, canals, churches. And I was wondering, what should I investigate now after my PhD, So my PhD advisor, Leo Kauenhofen, told me, have you heard about this amazing 2D material called graphene, which had been isolated just in 2004? And I said, no, I haven't heard about it. But then I looked at the papers, and they seemed really interesting. So what I did is I went to visit Andrei Geim and Kostya Novoselov to Manchester, so that they would, let us, into the tricks of how to do this Scotch taping and so on with graphene. And they were extremely kind. I went with a couple of friends from Delft, and they taught us, Kostya himself taught us how to do this graphene exfoliation, okay? And I've been deeply grateful to them ever since, okay? Because they were very generous with sharing tricks. It's not always that you share your tricks with everyone, including those who could become your competitors, But they were very generous. I think partly as a result of that, the 2D materials community is a very generous community where people share, all these tricks and they share physics and experiences. So after that, and after my postdoc at Columbia, I ended up back at MIT, where I started to do research on graphene. Now, what's so special about graphene? Okay, I've been talking a while already about graphene. Turns out graphene has many properties which make it a superlative. It has many superlatives. Extraordinary material. Okay? It is the strongest material that exists, the best electrical conductor, the best thermal conductor, is ultra thin and flexible, but at the same time very strong. It has many properties which make it very unique. One of the most unique properties is that electrons in graphene they propagate like ultra-relativistic particles, something closer to the way, particles propagate at CERN, in these high-energy physics accelerators. So you can kind of think of graphene at some level like, a giant, like a particle physics, accelerator or experiment going on in your lab, okay? Not this giant, Now, to give you an idea of how different the behavior of electrons in graphene is compared to normal materials, let's do these 3 experiments. We're going to do a classical physics experiment, then a quantum mechanics experiment, and then a relativistic quantum mechanics experiment, okay? Thought experiment. So let's look at the laws of classical physics. So who's the most famous classical physicist you can think of? Newton. Let's bring Newton, okay, here, and let's put a wall in front of, so let's give Newton classical tennis balls, not regular tennis balls, okay? And then let's put a wall in front of Newton. And then we're going to ask Newton to throw the tennis balls at the wall. What's going to happen? What do the tennis balls do? They just bounce back. Indeed, they bounce back all the time, okay? There is, the ball cannot go through the wall in classical physics. Now let's take, who's the most famous or one of the most famous quantum mechanics physicists? He has a famous equation named after him, Schrödinger. Let's bring Schrödinger, okay? Let's put a wall in front of Schrödinger, and let's give him quantum mechanical tennis balls, okay? So we're going to throw these quantum mechanical tennis balls at the wall. Turns out, when you do that, most of the times, the tennis balls bounce back. But every now and then, a tennis balls can make it through the wall in a process known as quantum tunneling. It's a very exotic thing, very confusing when it was beginning, at the beginning of the 20th century, it was thought of. Turns out all of our technology, all the technology, your cell phones, your laptops, all the modern technology works based on this, okay? So even though it's exotic, it all goes back to that, okay? You cannot understand the properties of a semiconductor without this quantum tunneling. Now, who's the most famous relativistic scientist? Relativity scientist? Einstein. Okay, let's do this ultra-relativistic physics experiment now. Let's bring Einstein, and let's put a wall in front of Einstein, and let's give him ultra-relativistic tennis balls, okay? What's going to happen now when Einstein throws the ultra-relativistic tennis balls to the wall? Turns out they always make it through, every single time, okay? This is a process known as Klein tunneling, okay? It was hypothesized, or predicted in 1929 by Oscar Klein, never to be seen because it's very weird, and particle physics experiments cannot give you this behavior. It's very hard to do, until electrons in graphene came. They behave like ultra-relativistic particles, and people directly measure this Klein tunneling in graphene. That's actually the reason why graphene is the best electrical conductor that exists. Electrons, when they propagate through graphene, they go through obstacles. They go through walls. In a normal material, the electrons bounce off obstacles, and that gives them high resistance. But the electrons in graphene, they go chup, chup, chup. They go through all the obstacles. And that's, I'm simplifying things, by the way. I see some experts doing like, I'm simplifying things. But that's largely the reason why graphene is the best electrical conductor that exists, okay? Now, graphene is not the only 2D material. There are plenty of 2D materials that exist and that we have been able to isolate. For example, hexagonal boron nitride is also a honeycomb, 1-atom thick material, but now instead of all carbon atoms, you alternate boron and nitrogen atoms, okay? It happens to be an electrical insulator. It's the thinnest, in fact, electrical insulator that exists. We also have materials like tungsten diselenide, which from the top also looks like this honeycomb of alternating tungsten and selenium atoms. This time, a single unit cell is 3 atoms thick, not 1 atom thick. This is a semiconductor, okay, with a band gap that changes dramatically with the number of layers, such that one layer emits color in one wavelength, 2 layers emit color in a different wavelength, for example. Yeah? So you see now that how the number of layers changes, the properties can change, and quite dramatically. Using this tungsten diselenide, for example, a few years ago, actually by now 10 years ago, in my group, we made the world's thinnest LED, less than 1 nanometer in thickness, and you see the light emission from this 1 nanometer LED shining at you. Now, not only we have many two-dimensional materials, but we can stack them on top of each other, okay? So stacking 2D layers is the new 3D. You can, for example, choose this particular combination of materials to stack on top of each other, or you can change and choose a different combination of 2D materials to stack on top of each other. And the properties of these heterostructures change depending on the order in which layers you choose to stack on top of each other. Yeah? So this type of studies, I once had a chef, Ferran Adrià, he was the world's best chef at some point, a few years ago, come to the lab. I was trying to explain to him the stacking, and suddenly at some point he says, oh, this is like a millefeuille, Now I understand, how the properties change, and when the combined structure tastes better than each of the layers, So, and indeed, it's a little bit like that. When you stack 2D materials on top of each other, people started to make these analogies to explain it to people. Oh, this is like, like Lego pieces, Legoland, Welcome to 2D materials Legoland. There were these papers, reviews by my friends and colleagues saying that you can stack 2D layers on top of each other the same way you stack Lego pieces on top of each other. And indeed, that's an important aspect of 2D materials heterostructures. However, I don't know how many of you play with Lego. I have small kids, so I play with Lego. And every now and then my son or my daughter comes and they say, Daddy, I cannot stack this Lego piece on top of the other. And I tell them, oh, you have to watch out. You have to precisely align to 0 degrees or 90 degrees the Lego pieces. Only then you can stack them on top of each other, okay? So this Lego aspect of 2D materials is quite nice, but I would say it's not the most unique aspect of 2D materials, because what we can do with 2D materials is something very different. We can do something which by now is known as Twistronics, which is that for the first time in the history of material science, as of a few years ago, when 2D materials came on the market, we can do the following. We can take a two-dimensional material, for example, graphene, and then place another two-dimensional material on top, for example, graphene on top of graphene, but we can do this with any twist angle that we want between the two structures. The same way I can put two cards on top of each other with any angle between the cards. Yeah? I can choose, for example, 30 degrees, 26 degrees, 1.1 degree, why not? As I will show in a moment. And the properties of the combined heterostructure can change absolutely dramatically compared to the properties of each individual graphene sheet. Yeah? And that's what I'm going to be telling you about. Now, so that you can visualize this, when you rotate these two structures, when you rotate two periodic structures on top of each other, you form something known as a moiré pattern. You can see this these soccer balls that you see, I'm going to pass around this thing. Mike, can you maybe? This is a moiré simulator, 3D printed in my lab. Okay, you can play with it a little bit, not for too long. It has to go to everybody, and I want you to pay attention to my talk. But you can play with it a little bit, and then we can, you can see the effect, that you get when you do that. I want it back, please. I only have one of them, okay? Okay, so we have discussed a little bit now about materials, about Legoland and Twistronics. Let's get a bit more serious into graphene, okay? Now, this is what happens when you rotate graphene on top of graphene. You form this moiré pattern where the moiré wavelength, which is the distance between the soccer balls that you see here on the screen, is sort of inversely proportional to the twist angle, okay? Now, that's what happens in real space. What happens to the electrons and to their energies and so on? Yeah? So let's do first the simple version, then I'll do a version for the specialists, okay? So what happens for graphene on top of graphene? Let's first look at the energy of the electrons in regular graphene. So if I take regular graphene, just one layer, and I plot the kinetic energy of the electrons as a function of their momentum, forget about these Greek letters. Yes, this is a function of momentum. Turns out it's a straight line. This straight line are something known as the Dirac cones of graphene, and it's the same energy momentum dispersion that you get, for example, with photons, with light, like the Dirac cones. The cones, for example, of the dispersion of photons, which Einstein's famous for. That's why photons go at the speed of light, regardless of their energy. This steep slope means fast electrons. Electrons in graphene go very fast, okay? That's the message. And their energy is independent. sorry, the speed, which is given by the slope, is independent of their energy. What happens, this is the reason why electrons in graphene behave like these ultra-relativistic particles. Okay? Now, what happens if we take twisted bilayer graphene at the magic angle, which is 1.1 degrees? Okay? The kinetic energy of the electrons versus momentum has this very flat, very small slope, which means that the electrons go very slow. Yeah? Now, why is that important, whether the electrons go fast or slow? Okay? If you have, we call this, by the way, flat bands. You will hear me say flat bands a number of times. It means this almost flat pancake, okay, for the energy of the electrons. So for fast electrons, okay, the Coulomb interaction, the repulsion, because electrons are charged particles and they repel each other, okay? The Coulomb interaction energy between them usually is very small compared to the kinetic energy. So one kind of ignores often that behavior due to these interactions. However, for slow electrons, now the electrons do not have much kinetic energy, so all that remains is that Coulomb interaction, okay? And the Coulomb interaction, therefore, acquires a disproportionate role in the behavior of the system. Now, why is this important? Okay? When you look at the emergent behavior of quantum matter, okay, turns out the behavior of a single object, like an electron spin there, is something which is simple. And by that I mean we understand it, theoretically. However, when you put many electrons together which are interacting with each other, that behavior is much more complex. The behavior of many interacting particles is difficult. In fact, we do not understand it theoretically. Okay? But turns out that the majority of the most fascinating states of matter that we have in the universe are actually due to these type of many-body systems, many particles which are strongly interacting with each other. That happens in the quark-gluon plasma, which is a state of quantum matter that occurs a few 100 nanoseconds or microseconds after the Big Bang, and that we can recreate nowadays in high-energy physics accelerators, like Brookhaven National Lab. It also happens in neutron stars, which occur after the explosion of supernova explosion. Those neutron stars have many interacting phases of neutrons, interacting with each other, and there are different types of phases of matter. It also happens on, in the phases of matter of correlated quantum materials, such as, for example, the high-temperature couplet superconductors. All of these behaviors are due to this type, and we do not understand them very well. So sometimes I do this analogy, which is not perfect, so the experts, please forgive me, but to explain the difference between, particles which move very fast and have large kinetic energy and particles which move very slow. This is like if you're walking in New York City versus a small town, So it is well known, people have done research with satellites on this, that people in New York City walk very fast. So they mostly walk past each other and they barely have time to interact, they don't talk to each other, Whereas people in small towns go much slower, and then you get to come close to someone and you start talking and interacting, and all kinds of things happen, when you talk and interact with people, okay? It's a little bit of that flavor, Particles that interact with each other change in their behavior, and they do many things which fast particles do not do, because they barely have time to interact with each other. Okay, so we have traditionally had two platforms to study strongly interacting quantum matter. One is regular quantum materials, where the typical length scale, the lattice scale, is an angstrom, or 0.1 nanometers. That's the typical distance between atoms in a typical material. Okay? This is an example of a high-temperature couplet superconductor. When you work with these materials, each time you have a different material, you have to grow a different crystal with a different chemical composition, very complicated elements and crystal structures, etc. And we have relatively little control over the properties of one particular crystal. You have to change crystal if you want to change something. About 20 years ago, people realized that you can make these lattices made of ultra-cold atoms in optical lattices. You shine two lasers, four lasers at each other. You create these periodic patterns that you can load with atoms. Here, the typical length scale is 1 micron, which is the wavelength of light. And you can, the cold atom physicists have exquisite control over all the parameters of the system. So they can control and tune everything much better than here. However, because of this large, this long length scale of a micrometer, it's very hard to realize many phases of quantum matter that you would like to realize because their atoms are a little bit too hot. It's very hard to cool them to the necessary temperatures to observe many of the phases of quantum matter that we like to see. And what I want to tell you about today in the remainder of the talk is about this new platform called moiré quantum matter. Well, it was developed over the past maybe 6 years or so. The typical length scale is 10 nanometers, okay? And where we have not quite as much control as in this platform, but a lot more than here. But we are able to observe many, many phases of quantum matter, as I will mention. So for the specialists now, so what is magic angle twisted bilayer graphene? Okay, so this electron, these Dirac cones of the electron, the electron energy momentum dispersion in layer of graphene number 1 and in layer of graphene number 2, this would be the behavior that would be realized if the electrons in one layer did not know that the other graphene layer exists. But in reality, when you put two graphene sheets on top of each other, these layers are only 3 angstroms apart. The electrons are very much aware that the other graphene sheet exists, and in particular, they can tunnel between the layers. Okay? That interlayer tunneling gives rise to a band gap opening there, okay? So hybridization. This is the same thing as bonding anti-bonding states in a hydrogen molecule, but this is bonding anti-bonding bands in a giant graphene bilayer molecule, okay? As this is the situation when this interlayer tunneling is much smaller than the energy of that crossing point. But as you decrease the twist angle, these two Dirac points get closer to closer, and this band, which gets pushed down by the band gap opening, gets pushed down to lower and lower and lower energies until at some point it touches 0. We say that a flat band condition has been realized. This occurs at an angle which was coined by Bistro and McDonald to be the the magic angle, and it is 1.1 degrees. I should mention that there were also earlier theoretical and experimental work which looked at the single particle physics, one electron physics of this magic angle graphene, already showing that there might be something interesting there in the many-body effects. Okay, so this is a cartoon. This is an actual calculation of the energy versus momentum. These are the flat bands, okay? Now, if we want to look at where are the electrons in this moiré pattern, okay, we have to go from momentum space to real space. And to go from momentum space to real space, you have to do a Fourier transform. And the Fourier transform of a very flat extended object is a highly peaked object, okay? So when you look, where do the electrons like to be when I place them in these flat bands? Turns out the electrons like to sit in certain regions of your moiré pattern. They're called regions of AA stacking, where all of the carbon atoms seem to be locally aligned between the two layers. Okay? These regions are separated by regions of so-called AB and BA stacking, where the electrons do not like to be. So from a schematic point of view, magic angle twisted bilayer graphene looks like this. We have these AA regions where the electrons like to be, separated by these AB and BA regions where the electrons do not like to be. In a slightly more realistic schematic, magic angle graphene looks like this. We have these two twisted layers. We have these regions of AA stacking where the electrons like to be. They're separated by about 13 nanometers. And then we have the in-between where the electrons do not like to be. This is going to be sort of an analog of my ultra-cold atoms lattice, okay, but in a real material. This is an analog of this triangular Fermi-Hubbard lattice. Now, triangular is in quotes here because in reality this is a honeycomb lattice because AB and BA are not the same thing, so this is a honeycomb lattice. And Fermi-Hubbard lattice is also not very precise because the electronic structure of magic angle twisted bilayer graphene has interesting mathematical properties called topological properties which prevent a direct mapping to the usual Fermi-Hubbard lattices of cold atoms. Okay, this is for the experts. Okay, so what happened then? Okay, we made these devices. Let me tell you first how we make these devices. Okay? So we start with, it's again a very simple process. We start with a glass slide with a polymer stack, sticky polymer. Okay? And then we bring a substrate which has hexagonal boron nitride. You remember that insulating material? This is now about 10 nanometers thick. It's not a monolayer, it's a little bit thicker. This is going to be a very convenient substrate for graphene. So we come with the sticky polymer, and we pick it up. Yeah? Then we bring another substrate, which has a graphene sheet on it. Okay? Thousands of groups can do this, exfoliate graphene onto a piece of substrate. And we position our hexagonal boron nitride sort of in the middle on top of the graphene, so that we come down and tear the graphene pieces into two pieces. Okay? From the top, this looks like our substrate with half of the graphene, and the glass slide with the polymer, with the HBN, and the other half of the graphene. But remember, these two pieces of graphene, they're at different heights, but they come from the same crystal of graphene. So the orientation of their atoms are correlated, because they come from the same crystal. So what we do now is we can rotate the substrate by any angle that we want, for example, 1.1 degrees, why not? And then we can shift it and place it on top, and we stack the two graphene sheets on top of each other. And we pick them up and continue our nanofabrication. But now we have created this moiré pattern between these two crystals, which are rotated by an angle of 1.1 degrees. Okay? Now, this is at the same time harder than you think and easier than you think. Okay? So, probably my grad students are hearing this. Easy? What do you mean? But a high schooler can come 2 days to the lab and learn how to do this thing. Okay? It's not super sophisticated. Getting it reliably, consistently, and making devices out of it is a bit harder. But we've done this with high school students. Okay, so we end up then with a device that looks like this. We have the twisted bilayer graphene at a magic angle, for example, is encapsulated between hexagonal boron nitride flakes. That is very convenient because it protects the graphene, and it's a nice dielectric. We contact the graphene with source and drain metallic electrodes so that we can apply a voltage and measure a current circulating through it. And very importantly, we have a metallic electrode, which is called a gate electrode. This gate electrode, together with the twisted bilayer graphene, they form the two plates of a parallel plate capacitor. When you apply a voltage to this parallel plate capacitor, you accumulate charge in the plates of the capacitor, which means we can vary the density of electrons in the graphene. Okay? And that's a key thing. For those of you who are experts, this is a field effect transistor geometry, FET transistor geometry. So what happened in 2018 is that we measured the conductance of these graphene devices as a function of density, and we saw that at some points, for some densities, this conductance was 0, but it was 0 for a device that should be a good metal according to single particle physics. Okay? Using simple quantum mechanics, this should be a very good metal. However, we measure, and it's an insulator. It's a special type of insulator called a correlated insulator, an insulator due to the strong interactions between the electrons in the system. And then, if we put a few extra electrons or holes, the material below a certain temperature stops dissipating energy and becomes a superconductor. Okay? This is something that only happens for angles 1.1 degree plus minus 0.1 degree. If you choose a different angle, none of these things happen. Okay? Remember, graphene is not an insulator and it's not a superconductor, but we put two things together, just a little bit of twist angle, 1.1 degrees, and it becomes things which it wasn't before. Yeah? So this is something, when my students show me these data, this is resistivity versus temperature and density, and this dark means superconductivity, and this thin is insulator. It reminded me of the hundreds of times that I had seen at seminar these data. Okay? This is the phase diagram of the high temperature cuprate superconductors, one of those unconventional materials which are not understood by theory. Let me flip the axis so that you get the same scheme as here. At 0 doping, which means actually 1 electron per copper atom in the cuprates, you have a correlated insulator called a multi-insulator. You dope with holes, you have a big superconductor. You dope with electrons, you have a small superconductor. In graphene, at 2 electrons or 2 holes per moiré unit cell, you have a correlated insulator. You dope with holes, you have a superconductor. You dope with electrons, you have a superconductor. Now, there are many similarities, but also many differences between these two systems. Okay? I don't want to stretch too much the similarities. But in particular, a big difference is that this is a theoretical phase diagram. To populate it with experimental data points, you have to grow hundreds of different crystals, each of them with a different chemical and disorder composition, often made of different materials because you cannot go from here to here using the same atoms. This is all done in a single device, in a single cool down, without introducing chemical impurities. And to go from here to here, I dial a voltage knob, in my voltage source. Okay, so this is a lot more tunable, and as you can imagine, it attracted a lot of attention. So we posted this in March 2018, coinciding with the March meeting of the American Physical Society, and then what I call the theory tsunami came, which is that this is a list of the papers that appear within a few weeks of us posting, our results on the archive. This list has now several thousand papers, okay? People went sort of crazy, They started to ask, okay, so what are the properties of these correlated insulators and what is the superconducting order parameter? So there were all kinds of proposals, with all letters of the alphabet. Could be S, P, D, D plus ID, P plus IP, F, I always joke that I came from the field of a single layer graphene, vanilla graphene, where the angular cone of disagreement between theorists is about 20 degrees, In this field of correlated physics, it's 360, In fact, it's 4 pi, it's in 3 dimensions, the disagreement. So this was quite a sociological experience for me, So I have to tell you that we do not know the answer to these questions yet. It's a very complex problem to analyze theoretically, but experiments are narrowing down fast the possible options. It's no longer that all of these things could be, okay? So experiments are narrowing down the options. Now, this thing generated also a lot of popular press attention and lots of articles with cool pictures, like speed meters and things like this, happen. Let me tell you what has happened, experimentally since our discovery. Yeah? So what happened since April, the paper was officially published in April 2018, and the first thing that happened is that we have reproduced our own results in my group. Believe it or not, it doesn't always happen that you're able to reproduce yourself. It's very good when you do, but experimentalists, I see you all smiling, right? You don't always reproduce yourself. Now, we have made a lot more devices, and by now this is, established technology in our lab. But much better than you reproducing your own results is when other groups, independently of you, reproduce your results. Only then it becomes real science, real physics, okay? Unfortunately for us, there have been dozens and dozens of groups around the world that have reproduced and extended our results to other systems and to many interesting systems. Another thing that has happened is that we have measured a lot of phenomenology which is typical of these correlated unconventional quantum materials in our systems, like strange metal behavior, nematicity, Fermi-Sefer reconstructions and cascades of phase transitions, pseudogap physics, etc. I'm sure the experts are seeing many of the things that they study here. They have all been seen in these type of structures. We have also discovered many other correlated materials systems based on moiré patterns. Okay, it's not only graphene on graphene, magic angle twisted bilayer graphene. It's also ABC graphene on hexagonal nitride, magic angle twisted bilayer graphene. We call this twisted bi-bi, 2 layers twisted on top of 2 layers, but these 2 layers, each of them has 0 angle, but we twist between them. We also have moiré transition metal dichalcogenides, like those tungsten selenide structures that I mentioned earlier that give you the LED behavior. You can also slap them on top of each other and twist them, okay? Moiré TMDs, etc. One thing that has been very interesting has been the observation of ferromagnetism, anomalous Hall, and integer and fractional quantum anomalous Hall physics in these structures. And that has brought this branch of mathematics called topology front and center to this problem in physics, okay? In fact, one of the nice things, that I have experienced in these past 6 years is that this moiré quantum matter field has meant the merging of several modern condensed matter communities that did not interact so much with each other before. You have the 2D van der Waals materials and heterostructures community, people that did graphene like myself. You have people that studied strongly correlated materials, cuprate superconductors, heavy fermions, pnictides, all these people. And the people that studied topological condensed matter physics, physics of the quantum Hall effect, topological insulators, Waal semimetals, all of these 3 communities come together in this problem of moiré quantum matter. Huh? These structures, these moiré patterns, are accessible, are at the surface, and they are really prime candidates to investigate with scanning probe microscopy, with scanning probe systems, local probes. So scanning scanning tunneling microscopy, scanning nanosquid, scanning single electron transistor, scanning near optical microscopy, scanning transmission electron microscopy, etc. All these techniques have been applied and visualized these moiré patterns and studied their properties, etc. Moreover, new techniques have been invented based on this moiré pattern. For example, there's something called the quantum twisting microscope. The way we fabricate our devices, I took one graphene piece, right, split it in two, put it on top of each other, rotated. The angle was fixed when I made my device. Nowadays, people can make these two pieces, put it together, and in situ rotate the angle continuously and study the properties of function of angle electronically in situ while the sample is cold. This is a huge development in the field, and many people around the world are building these quantum twisting microscopes. This is last year's development. The other thing is that we're building the next generations of moiré quantum matter. We did this with 2 layers, but why not put 3 or 4 or 5? And twist all the angles and try all possible combinations. So we call this moiré magic 3.0 and beyond. And in fact, a few years ago, both my group and my postdocs group, Professor Philip Kim's group at Harvard, we posted back-to-back papers in Nature and Science with the discovery of magic angle twisted tri-layer graphene, okay? Where the magic angle is different. It's not 1.1, it's 1.7 degrees, 1.6 degrees actually. And it happens to be an even more phenomenal superconductor than the bilayer case is, and much more tunable. So with this, I want to end with some of the outlook about how is this field evolving and what it has become. So I told you that we have these 3 platforms to study correlated materials and topological physics. It turns out with the magic of this moiré quantum matter platform that is just so tunable, in the span of just a few years, we have been able to realize all of the known phases of quantum matter that exist, all of them, just by tuning this and varying the density of electrons. We have realized novel correlated insulators, unconventional superconductors, many topological phases, magnetism, moiré quasi-crystals, new ferroelectric materials, strange metals, Wigner crystals, excitonic insulators, pneumatic systems, etc. And in fact, we have discovered a few new phases of quantum matter that didn't exist before just by using this platform. Okay? We can do this all with very simple materials, just like graphene on top of graphene, or twisting transition metal dichalcogenides, very simple materials. But all of these things that I told you about before was basically twist electronics, okay? However, moiré magic is spreading to other fields and into, beyond twist electronics. For example, the cold atoms people, they said like, oh, we can also twist lattices, why not? So there is this thing called moiré and twisted cold atom lattices, started with theoretical predictions by Ignacio Ciriac, one of the leaders in the field, and now a group in China recently made the first, atomic cold lattice with twisted bilayers, in the system. The trick to slow down the kinetic energy of the electrons, the speed of the electrons, can be also done to slow down sound, phonons. So there is this field of moiré and twisted phononics, where you can also bring, by twisting appropriately, vibrating plates or phonons, at the microscopic scale, you can slow down tremendously the speed of sound. And you can do all kinds of tricks. You can imagine, not having sound propagate can be very useful for many things. Okay, so there is this field also. They call it magic angle bilayer phononic graphene, acoustic twisted bilayer graphene, etc. Moreover, the exact same trick can also be applied to light. So there is this thing called moiré and twisted photonics, where you can slow down tremendously the speed of light, make it almost 0, which you can then use to do all kinds of nonlinear optical phenomena. This is perhaps, other than the electronics, this is the fastest growing field. With the Department of Defense entire programs based on this moiré and twisted photonics, people make photonic lattices and twisted them and slowing down light and doing all kinds of things. Yeah? But why stop there? Turns out these moiré patterns locally have very interesting chemical reactivity patterns, actually, and activity. So there is this thing called moiré and twisted electrochemistry and catalysis. In fact, one of the pioneering works is here at Berkeley from Kwabene Abediako in the chemistry department. He made electrochemistry locally on this moiré pattern, and he saw that there's different chemical reactivity of the different sites in your moiré pattern. Very interesting study. I really like this work. And my colleague Liang Fu, together with Claude Fersel and Yang Sun, predicted that these moiré metals patterns can be extremely good for catalysis for hydrogen production, etc. And then, of course, the high energy theorists also thought that they should be doing something. So there is this field called moiré gravity and cosmology. So you have, it turns out that this twisted valley graphene physics, there is an analog, to, space, time deformations, that perhaps may teach us something about gravity and cosmology, and, they also very creative. So with this, I want to end with, what I think is the most important slide. A lot of this work was done by my former graduate student, Yuan Zhao, who, as Mike mentioned, is now a professor here at UC Berkeley, okay? Together with Jane Park, Danny, and also some other people, lots of collaborators at MIT and at many other institutions, lots of support from various funding agencies, which I appreciate a lot. And as of a few years, we're back to these meetings in person, which I'm also very happy, and I want to thank you all for your attention. And I'm happy to take any questions.
Any questions?
I think there's someone running with a microphone, but
I have actually many questions, but let me ask the first one. Why is the... Well, but maybe before I can even start with a comment, because I'm old enough to live through the discovery of the high TC superconductors. And so something like 30 years ago, after high TC superconductor was discovered, the explosion of theoretical papers was probably 10 times higher than what you have seen. And of course, eventually, most of them turned out to be wrong. And I think the same thing will happen here. Well, I'll come back to my question. My question is, why when you are in the superconducting state, your TC is so low compared to the high TC superconductor? Can you make a conjecture as to how high TC you can achieve using your technique?
It is true, that's a very good question. It is true that the absolute value of the critical temperature is relatively modest, 1, 2 Kelvin, actually was the best samples. However, remember that this is a structure where the electrons are 10 nanometers apart. This is, the way we characterize superconductors, physicists, one way is to look at the absolute value of the critical temperature. That's very important, for example, for applications. But from a physics point of view, it's not the most relevant quantity. The most relevant quantity is how high is your critical temperature compared to how high is your Fermi temperature. What is the density of electrons that you have in your system? And it turns out that the ratio of the critical temperature to the Fermi temperature in these moiré superconductors, in magic angle, bilayer, and trilayer graphene, is the highest by far of any material. In that regard, they are the highest temperature superconductors known by far, much more than the cuprate superconductors. Theorists do not understand yet how come that a lattice which has 1 electron every 10,000 atoms is super dilute with Fermi temperatures which are many orders of magnitude smaller than typical metals, like aluminum, can have a pairing glue so strong that it gives you a TC which is higher than aluminum, okay? So this is something that theorists are still trying to understand. We all are trying to understand, because if we understood it, we could try to implement those design principles into materials at regular Fermi temperatures, metallic-like Fermi temperatures, and then the critical temperature would be well above the room temperature, if we maintain that same pairing glue strength, okay? So this is something which is an interesting question, but, in many respects, moiré, magic angle graphene is a super high temperature superconductor, by that ratio. Yeah? In terms of how high the absolute value of the critical temperature we could do in these moiré structures, so we have made 2, 3, 4, 5 layers. TC keeps increasing when you put more layers, but the extra TC increase diminishes, So it's given essentially by the ultra strong coupling limit, So at the densities that we have, it will not go above 3, 4, 5 Kelvin, okay, for these structures. But remember, the density is orders of magnitude smaller than for a regular metal.
Hi, thank you for such a great talk. I'm really curious about the quasi-crystal aspect. You said that you made quasi-crystals. I'm curious about, one, how you make a quasi-crystal in this platform, like from the Scotch tape level up. And I'm also curious if those materials superconduct.
So we have made various types of quasi-crystals, okay? Both, a quasi-crystal is a quasi-periodic crystal. And in general, when you twist two layers, two sheets of graphene, for example, most angles are non-commensurate. So these structures, the moiré pattern is periodic, but at the atomic scale, it's never actually truly periodic, okay? So in that sense, they're quasi-crystals. But you can also, even if you're thinking, oh, what about those, the more exotic example of quasi-crystals of these forbidden symmetries quasi-crystals? Well, it turns out you put graphene on top of graphene at 30 degrees, it's a dodecagonal quasi-crystal. So, even by a more narrow definition of quasi-crystal of this forbidden symmetry structure, you can also make them. These quasi-crystals, okay, of the non-periodic, non-commensurate angle types, we have also made them in superconducting form. So we have a paper in Nature last year about superconducting quasi-periodic crystals using twisted, in this case, tri-layer graphene with different twist angles between the first and the second layer and between the second and the third layer.
Hi, wonderful talk. Man, what a field. Do you have a favorite theory about it, why it would be 1.1, or is there, that's it. Do you have a favorite theory, or is there many theories?
So the prediction of the magic angle being 1.1 degrees is something that indeed was theoretically, well, truth to be told, there were experiments already showing that something interesting was happening at 1.1 degrees, and then theorists quickly realized that it was the formation of those flat bands, okay? So that's something that depends on the interlayer tunneling between two graphene sheets. For example, they're having some interesting experimental papers where they apply pressure to the bilayer graphene. That increased the interlayer tunneling because the layers were closer together, and that changes the magic angle condition. The angle is no longer 1.1 degree, it's a bit different from that, okay? And that was also theoretically predicted what would be the pressure dependence of the magic angle condition. So theorists do understand why this happened. That is basically, a simple way of thinking about it is the electron at the magic angle is not sure, it's as easy for the electron to conduct through the layer that it's flowing as to jump to the other layer, okay? And when it's, it doesn't know what to do, whether to continue from the same layer or to jump to the other layer, and there's an interference process that generates those flat bands, yeah? But this is something that was, theoretically predicted, the single particle behavior of having flat bands. Superconductivity and all those other things, it was not predicted, okay? That was a surprise, that we didn't expect.
Are there any implications for computer chips or fabricating computer chips and making it cheaper or more effective?
So, for now, this is all just wonderful curiosity-driven science, and we're learning a lot of things, okay? People ask me all the time, but it's beautiful science, good, but are there applications? Well, you can think of many things, okay? Right now, the biggest difficulty in making applications is the fact that we cannot make 1 billion magic angle graphene devices or identical, okay? That's technology that doesn't exist, okay? You have to think that this is kind of like taking plastic wrap, kitchen plastic wrap, tearing a sheet, putting it on the table, now splitting it in half and put it on top of another without a single wrinkle, not a single atom separation between the two sheets, not a single wrinkle, etc. That's something that we cannot do on big scales to make 1 billion magic angle devices that would all work the same. But let's imagine for a moment that we managed to do that, okay? This is an electrically tunable superconductor, okay? So superconductors are used in many technologies. For example, quantum sensors, single photon detectors. The best detectors of light are made with superconductors. This is the thinnest and the best single photon detector that exists in the world. It's just that we cannot make millions of them. But at single device level, this has been already researched by several groups. It's the thinnest superconductor that exists, and it's also the lightest. It responds the fastest to light, okay? On top of that is an electrically tunable superconductor. Tunable superconductors, our chair here, studies them for superconducting qubits. Right now, a lot of the superconducting community, qubit community uses aluminum, which is a TC similar to magic angle graphene. Magic angle graphene is electrically tunable. You can make all your elements of your superconducting circuit, including capacitors, Josephson junctions, and all those things, all electrically tunable. Okay, you can shut them off as you want, etc. No one has made a magic angle graphene superconducting qubit, but who knows? If we make one, and some groups are trying, it could perhaps have better properties or more tunable because you can tune, the critical temperature, for example. Okay? So there are many things that if we could fabricate these things at scale, might be possible in terms of technology, okay, for either quantum computation or for even classical superconducting and cryogenic electronics. But this biggest obstacle right now is engineers growing these, fabricating these devices on large scales.
Thank you for the nice talk. I want to ask, is the carbon a special element to help us see so many diverse phenomena? Can we see these phenomena on other elements, two-dimensional elements? Thank you.
Very good question. So graphene is a little bit special, okay? People have seen this correlated physics and many of these phases of quantum matter using also other materials, for example, twisting transition metal dichalcogenides. Graphene is a little bit special because of the symmetry properties of the honeycomb lattice, where all atoms in the honeycomb, in the hexagon, are carbon, okay? That gives it the special symmetry properties that lead to these Dirac cones, which then, when you couple two of these Dirac cones, give rise to those flat bands at zero energies, okay? So for example, the critical temperature of electrons in graphene is the highest of any of these moiré, superconductors and so on. But other systems are also very interesting. They're less sensitive to the twist angle. For transition metal dichalcogenides, anywhere from 2 degrees to 5 degrees, you have magic physics happening, for example. Okay, so they're easier to make in some sense. And a lot of people are studying them. They also are good optical emitters, which graphene is not. So you can study all of this physics, not just with electronic transport, but with optics also, which is very interesting. So by now we have hundreds of two-dimensional materials, and everybody's twisted everything on top of each other, just to find interesting physics, So we need lots of graduate students, with good hands,
Hi, Professor. Thank you for the talk. I was curious about chirality in carbon nanotubes, and if you think that could be applied to a similar thing and get those moiré patterns. I know that certain chirality formats can be engineered into carbon nanotubes, and if that would be able to see a similar effect, or if you think that constraint in the rolling dimension would prevent some of those properties. Thank you.
Very interesting question. I did my PhD with carbon nanotubes, actually, okay? So in carbon nanotubes, which is, you take a graphene sheet and you roll up seamlessly into a cylinder, turns out you can roll it along different directions, okay? And that leads to something which is known as chirality in the carbon nanotubes. So there has been very little studies, okay? But there are a couple of papers where people theoretically have already thought about double-wall carbon nanotubes. What happens if I take two carbon nanotubes, two seamless cylinders, concentric, and I have different chiralities such that I have a magic angle between them, okay? So that's a very interesting thing. Very little studies theoretically, no studies experimentally so far, but it's a very interesting topic. On the issue of chirality itself, that's also very interesting because these structures, when you put them on top of each other, you can, let's imagine you make something with an angle theta and then theta, 2 theta, 3 theta. This is a chiral structure. You can do theta, 2 theta, 3 theta, or theta, 2 theta, 3 theta, left-handed or right-handed, okay? And chirality is a very interesting topic in chemistry and in physics too. So the properties of these structures, can be modified to couple to chiral molecules in different ways and for catalysts, et cetera. And it's a subject of very recent exponential increasing interest, in the community.
Question? This is maybe a second or third order question. Does isotopic variation?
Sorry. I hear a voice, but I don't know where you are. Oh, in the back, all the way in the back. Okay, good.
Does isotopic variation have any play here, especially in the moiré situation, or does it have an effect? If not, or if it does, can you take advantage of it?
Excellent question. So carbon is a material that appears on mostly two isotopes, carbon-12 and carbon-13, okay, carbon-14, but that's radioactive. And there have been very few studies of isotopic composition of these moiré heterostructures, okay? It is very interesting for many reasons, you know. First of all, you can purify graphite. I mean, you can actually grow isotopically purified crystals of graphite so that we could get carbon-12-13, purely carbon-12-13, or purely carbon-12 graphene, or purely carbon-13 graphene. And the isotopic composition plays an important role on many things. In conventional superconductors, also in unconventional superconductors, there's an isotope effect, changes the critical temperature. When you do thermal, you know, conductivity of materials, isotopically pure versus isotopically disordered materials, their thermal conductivity varies by a lot, okay? So it is something which is very interesting. No studies so far, mostly because there's so much low-hanging fruit that is being picked up, you know, first, and those studies are a little bit more complicated. You know, you need a source of isotopically pure, you know, graphite. But I'm sure they will come, you know. Several groups have already contacted me telling me, in fact, I have crystals in the lab of isotopically purified. And the moment a good student or postdoc wants to try it, you know, I'll tell them, yes, you know, go for it, because I think it's quite interesting.
You said that it makes a very good photodetector. Can you quantify that in terms of how is it compared to a photomultiplier tube?
So, you know, so I cannot give you, you know, numbers for these things, but there are papers that can provide you those numbers. The thing is, you know, it is a very good, so the best technology nowadays to detect photons, single photons individually and count them are these superconductors, you know, transition edge, you know, superconducting single photon detectors, where you bias your superconductors close to the critical current, and when a photon comes, and typically they are sensitive to extremely small energies, you know, so they're good for, you know, we have very good photodetectors of visible light, but of mid-infrared, far infrared, terahertz, much, much worse, okay? So when a photon comes, it heats up, it creates a local hot spot on your superconductor, which then becomes resistive, and that propagates, makes the superconductor normal, and gives you spike in voltage, and then it cools down again. You want it to cool down again fast, so it becomes superconductor again, and it can detect the next photon, and you can count them. Okay? Graphene, magic angle graphene, because it's the lightest superconductor, it's made of carbon, it's the lightest superconductor and the thinnest superconductor, it recovers extremely fast. It also helps that all the energy scales for what I showed there in graphene are extremely small energy scales, so it's very sensitive to even terahertz photons, okay? So for many reasons, it's actually an outstanding single photon detector, actually not only the superconducting regime, also as a bolometer and, you know, at ultra low temperatures. Yeah, I cannot give you efficiency numbers and things like that. My engineering friends, you know, we have to give you those, but papers are published already on the performance and comparison.
What happens if you introduce defects in the structure, like nitrogen vacancy centers in diamond?
Sorry, can you repeat?
What happens if you introduce defects in the structure of the graphene?
Very good. So, you know, graphite, you know, Mother Nature produces these graphite crystals, and they're extremely good. You know, I mean, if I ask Mike how many times he goes around and he can find an atomic defect, like a vacancy of a carbon atom in graphene, probably he tells me almost never. You know, it's extremely rare, okay? So, but remember, graphene is a conductor, okay? So, to the best of my knowledge, people don't tend to speak about optically active defects in graphene. However, in other 2D materials like hexagonal boron nitride, you know, defects in HBN are actually now very interesting and being looked at, you know, in the same way as nitrogen MV centers, you know, because, you know, they're very good, you know, defects for, you know, quantum sensing, you know, and they have different properties from the MV centers or from defect color centers in silicon carbide, etc. So there are many groups that are studying the properties of, you know, defects on HBN. In transition metals like chalcogenides, which are semiconductors, you can also, you know, you find also optically active defects. In graphene, they don't tend to be optically active because they're embedded in a conductor, in a metal.
Hi, thanks for the great talk. So I go back to your apple orange thing in 2D. So like you're looking at the superconductor right now, but now the superconductor is in 2 dimensions instead of 3 dimensions. So as we know, like the superconductor is less stable in 2 dimensions, like they have very different properties. I think you made like other like electronic devices like Josephson junction already out of the superconductor. So I wonder like what happened. Sorry, what do you find? Like, what do you find interesting, like in the future study when you look at those like 2D superconductor on like Armstrong thing, like the structure? Yeah.
Very good question. Remember I told you there's a mathematical, there's a theorem in physics that says that 2D materials should not exist. There's another one which says that 2D superconductors should not exist, that 2D magnets should not exist. Now, ignore all of them. They all exist. 2D superconductors, 2D magnets, all of them, okay? That's usually because the conditions for the theorem to apply do not apply to real life, okay? So we always find loopholes or exceptions. In general, if you take a 3-dimensional superconductor and you make it thin towards the 2D limit, the vast majority of superconductors, but not all of them, they weaken, okay? Because indeed, they don't like 2-dimensional order, okay, systems. The properties of 2-dimensional superconductors are very different than those of 3-dimensional superconductors. For example, the typical thing that you want, if someone tells you, I got a superconductor, they will ask you, does the resistance go to 0? And does it exhibit the Meissner effect? Does it expel magnetic field from the bulk? That's the typical characterization. Those 2 things you need for a 3-dimensional superconductor. In 2 dimensions, because there's no bulk, you cannot expel the magnetic field from the bulk. So the magnetic field actually penetrates. There's no conventional regular Meissner effect for 2-dimensional superconductors. And 0 resistance, you can get 0 resistance for various reasons, not just superconductivity. So how do we know that magical graphene is actually a superconductor? It exhibits 0 resistance, but no Meissner effect. Well, there's another thing that you can use, and that is the Josephson effect. Yeah? The Josephson effect, an oscillation of the critical current when you apply a magnetic field in a junction made with whatever superconductors, 3D or 2D, okay, is a phase-coherent phenomenon that it's known to only happen for superconductors. And the Josephson effect has been measured. We already reported it in our original paper, and it has been measured and confirmed and designed by many people. Now, the Josephson effect is special in 2D materials. Now, this is a little bit for the experts. But in the Josephson effect, typically the dimensions of your junction tells you what's the distance between the minima and the oscillations of your critical current. But in 2-dimensional superconductors, there is a different length scale. It's not the dimensions of your junction. There is something called the Pearl length that determines what is the distance between the minima and your critical current, and that has been seen, I believe, for the first time in magical graphene superconductor devices, or best characterized in this type of 2-dimensional superconductors.
Any last questions? All right. Okay. So that was pretty good.
Thank you very much.